Hi everybody! So in this video we're going to talk about dienes. So a specific group of molecules. They are called dienes because of what's present in the molecule. So if you see me looking down, that's because I'm drawing on my surface down here. But the name diene, there is the end of the word "ene" or "enes", you might remember, that tells us that we have a carbon to carbon double bond. And then the prefix di tells us we have two carbon to carbon double bonds. So a diene molecule is a molecule with two carbon to carbon double bonds. I have a couple of examples written down here. So I have the names written out and we will draw the molecules. First example is 1,3-butadiene. This molecule has 4 carbons, and I know that from the but part of the name. It has a double bond on carbon 1, so if I go left to right, that's this carbon here between carbons 1 and 2, and then a double bond on carbon 3, so right there. So that's an example of a diene. Another example is E13-hexadiene. So here we have 6 carbons. We have a double bond on carbon 1 and a double bond on carbon 3. Another example, E14-hexadiene, 6 carbons again, double bond on carbon 1, double bond on carbon 4. So dienes represent a specific group of molecules that have a specific property we'll call conjugation, and I'll explain what that is. That whether or not the molecule has conjugation depends on where the double bonds are in the molecule. Having conjugation impacts the stability of the molecule, and we can observe that through the delta heat of formation values. So 1,3-hexadiene and 1,4-hexadiene both have the same number of carbons and hydrogens present in the molecule. But the delta heat of formation for 1,3-hexadiene, now let's talk about what this is. Delta heat of formation is the energy released or absorbed. I'll write out the word energy here so we don't confuse it with E double bonds. So the energy released or absorbed during the formation of a pure substance from its elements. So this is covered in more detail in general chemistry, but that's what the heat of formation is. So we have a different heat of formation value for different molecules. For 1,3-hexadiene, that value is 54.4 kilojoules per mole. And for 1,4-hexadiene, it is 74.1 kilojoules per mole. So two molecules with the same number of elements have quite different delta heat of formation values. And this difference tells us that the 1,3-hexadiene is about 20 kilojoules per mole, or requires about 20 kilojoules per mole less energy to form. So this is a more stable molecule. Just because of that placement of the other double bond. This is a more stable molecule, and this is due to conjugation. Conjugation occurs when we have overlap of multiple 2p orbitals. So 1,3-hexadiene has conjugation, but the 1,4-hexadiene does not. 1,3-butadiene also has conjugation present, and so we'll look at that molecule first. It's just a little bit simpler than 1,3-hexadiene since we have 2 fewer carbons. But let's kind of investigate this molecule, use what we know about the molecule to understand why conjugation is present and why that's more stabilizing for that molecule. So if we have 1,3-butadiene, a little bit more detail about this molecule. I'll redraw that skeletal structure where we have 4 carbons in a chain and then 2 double bonds. One thing you should remember from Organic Chemistry 1, and I'll expect you to remember, is being able to identify the hybridization of different molecules, or different atoms in different molecules. And so we do that by counting electron-dense areas. Each carbon in 1,3-butadiene has 3 electron-dense areas. It has 1 double bond and 2 single bonds. 3 electron-dense areas means that atom has a s orbital and 2 p orbitals hybridized. So it has sp2 hybridization. So in 1,3-butadiene, that is the hybridization of each carbon atom. Each carbon is sp2 hybridized. When we have an sp2 carbon, its bonds are in a plane. So all 3 bonds can be in a plane like this. You can view it in different ways, but it will say that all 4 carbons in 1,3-butadiene are in a plane, or all in the same plane. If you have a molecular model kit, you can draw that out. You can look at models online to see that this is a planar molecule. Now with each carbon being sp2 hybridized, that also means that each carbon has an unhybridized p orbital. And remember, unhybridized p orbital, those are where pi bonds exist between these unhybridized p orbitals. In order to have a pi bond, the atom must have an unhybridized p orbital. So let's draw out, we're still drawing 1,3-butadiene, but with some different detail. So let's draw the 4 carbons and just the single bonds right now. So all 4 carbons, there are single bonds between the carbon, sigma bonds, and then the carbons on the end are bonded to 2 other hydrogens. The 2 carbons in the center are bonded to 1 hydrogen. So if you look at 1,3-butadiene and you ignore just the pi bonds for now, you should be able to draw out these single bonds with the implicit hydrogens. Now we said each carbon has an unhybridized p orbital. If we have a planar molecule, like I said before, so all the carbons are in one plane, then the p orbital that's unhybridized is perpendicular to that plane. So I'll draw the p orbitals as being above and below where the single bond lines are. So each carbon has an unhybridized p orbital. I'm using different colors to show the top and bottom lobes. But each p orbital has one lobe above the chain of carbons and one lobe below the chain of carbons. So again, this is where our pi bonds exist. We have a pi bond between carbon 1 and 2. We can draw that with these lines to show that these p orbitals are overlapping. We have a pi bond between 3 and 4, and we can draw those lines to show that pi bond existing. So just to add detail to the written notes, what we've drawn here are the p orbitals which is where pi bonds exist. When we draw this molecule in this way, we're drawing each individual p orbital for each atom that has an unhybridized p orbital. But in reality, these p orbitals are completely overlapping with each other. All of the blue lobes on top of the carbon chain overlap with each other, and all of the green lobes that we've drawn under the carbon chain overlap with each other as well. So we draw them as the individual dumbbell lobes, but really they're overlapping. So in reality, the p orbitals overlap. So let's redraw what that looks like. We'll do the 4 carbons again in the chain. Can draw the hydrogens. Since we're drawing out the carbon atoms, we should draw hydrogens. Now, instead of drawing the dumbbell shapes for the p orbitals, we're going to show that these p orbitals overlap across all carbons. And they can do this because each carbon in this chain is sp2 hybridized, so each carbon has that unhybridized p orbital that can overlap with the carbons adjacent to it. And this is what we call conjugation. Where we have a larger p orbital system that these electrons can exist in. The pi electrons now are not located to one atom. They can be shared across all of these atoms. So having more space for electrons to move around is more stable for a molecule. So this is why we have a lower heat of formation for molecules that have this conjugated system.